Hello everyone, I'm Lynn Trong with the National Renewable Energy Laboratory, and I'd like to welcome you to today's webinar hosted by the Building America program. We are excited to have Dr. Ian Walker here today to discuss what makes high-performance homes different from a ventilation perspective and how they might need to be treated differently than traditional construction. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. By doing so, we will eliminate the possibility of feedback and echo. If you select the telephone option, a box on the right side will display the telephone number and audio pin you should use to dial in. If you have technical difficulties with the webinar, you can contact the GoToWebinar help desk for assistance. If you would like to ask a question, please use the questions pane to type in your question. If you're having difficulty viewing the materials through the webinar portal, you may find PDF copies of the presentation at the website listed here, and you may follow along as our speaker as Ian presents. Today's webinar is being recorded, and the recording will be available on the DOE YouTube channel within a few weeks. We have an exciting program prepared for you today that will cover several topics, including combustion safety, identifying indoor and outdoor key pollutants, filtration and insulation, durability, and maintenance issues. Specific guidance will be given for recommended systems based on climate, single versus multifamily, envelope tightness, and the presence of central forced air heating and cooling. The webinar will conclude with a look to the future of high-performance ventilation systems. Before our speaker begins, I'll provide a short overview of the DOE Building America program. Following the presentations, we'll have a question and answer session, closing remarks, and a brief survey. The U.S. Department of Energy Building America program has been a source of innovations in residential building energy performance, durability, quality, affordability, and comfort for more than 20 years. This world-class research program partners with the industry to bring climate-specific guidance and resources to market. Visit our website at buildingamerica.gov to find more information about the program and the Building America Solutions Center, which provides expert information on hundreds of high-performance construction topics, including air sealing and insulation, HVAC components, windows, indoor air quality, and much more. Building America is supported by 10 industry research teams and 4 national labs. Each of these teams and labs partner with dozens of industry professionals, including builders, remodelers, manufacturers, and utilities. The best and the brightest in the residential buildings industry can be found here. And now on to today's presentation. Our webinar today is Ventilation Strategies for High-Performance Homes, Part 1, Application-Specific Ventilation Guidance. If you would like detailed information about this effort, please feel free to contact our speaker. Our speaker today is Dr. Ian Walker, a scientist at Lawrence Berkeley National Laboratory who leads the Residential Building System Group. With more than 20 years of experience as a building scientist, his current work focuses on indoor air quality, retrofits, zero to low energy homes, and HVAC systems in residential buildings. He is an ASHRAE Fellow and serves on standards and technical committees for ASHRAE, American Society of Testing Materials, Residential Energy Services Network, and Air Conditioning Contractors of America. With that, I'll hand it over to Ian. Thanks, Ian.
Thank you very much for that lovely introduction. I'm going to start out today with a little bit of background to basically think about, before we get into specifics about individual house types and climates and so on, you know, why would we be ventilating anyway? And basically, we want to remove or dilute pollutants in a home, and pollutants can either be health rated or not. For example, moisture is the traditional thing that has been ventilated for many, many centuries, if not thousands of years, where we have moisture generated by all sorts of activities, and we try to control that through ventilation. Then there are odors generated by people, the things we do, from cooking, from stinky sneakers. We'd like to also live in places that are not offensive to us from the perspective of odor. And then we think a little bit more about health-related pollutants. Some recent work has been done to figure out of these sort of chemical soups that we live in, and there are a lot of chemicals in our built environment. We find that The vast majority of them, though, are at very low concentrations. They're not at concentrations that are a health issue. And a few pollutants have come up to the top as ones that are prevalent in many, many homes and are prevalent at levels that we worry about from the perspective of health. And they are particles that mostly come from combustion, formaldehyde that we find in building materials, and sometimes the contents of homes in furnishings and things like that, and also NO2, oxide of nitrogen, which again is primarily from combustion. Those are the three major health-related pollutants of concern, and the reason why I wanted to highlight these three is that when we're thinking about how we ventilate and how we are going to address indoor air quality in high-performance homes, it's good to think about exactly what are our targets and what are the things that we want to put our efforts into. One last note here is that for a long, long time, perspective has been that we'll use the outdoor air to remove or dilute these indoor pollutants. However, we also know that there are sources of pollutants that are outdoors. Particles and ozone are the ones that are probably most prevalent that most of you will have heard of. The Environmental Protection Agency regulates, or I should say tries to regulate, the concentration of these pollutants in the outdoor environment, but they are often at levels that are high and are high enough to be of concern from a health perspective. And so we can't just simply think about bringing lots of outdoor air into a home. We have to think sometimes about what's in that outdoor air also. So that's a little bit about the sort of things that we think we're going to control with ventilation. And I'm going to talk a little bit about, so, you know, what are our current sort of best practice? How do we think we're going to do this? I should tell you that I have put a little graphic there of the ASHRAE 62.2 standard, and I am the current vice chair of that standards committee. And we have a committee of just over 20 people with a wide range of expertise who are working on this national standard for indoor air quality. And I'll refer to that throughout this talk here today, because it sort of provides a touchstone for what we're talking about. And it's used in many voluntary programs, some states required, and so on. And it's become sort of the de facto standard. But I want to emphasize that this is the minimum performance standard. This is not talking about the best systems you can install in a house. And so the 62.2 standard is about what is the absolute minimum, what's the worst we will let you do and say you're doing something acceptable indoor air quality. So that's an important perspective that we need to keep in mind in this discussion here today. So I talked about pollutants that often come from things like cooking. And if you have a kitchen, probably most of you have a range hood. And we like this idea about local exhausting these pollutants right where they're generated. So for kitchens, you have cooking moisture, odors, and combustion. And combustion comes from both if you've got natural gas and you're burning it, but also from the act of heating up food. If you're frying a steak or frying onions or something, there's lots of particles and combustion products coming from that. And also, we put exhaust systems in bathrooms, mostly for moisture and odor control, although one could consider if you have cleaning products in the bathroom that might have chemicals in them that you don't want to be breathing, you could be ventilating for that also. But local exhaust is a pretty widely accepted way of dealing with some of these pollutants for particular rooms, in this case kitchens and bathrooms. But for all the other pollutants that are sort of spread out throughout the house, we have to think about what we call whole house ventilation, which is for everything else. So once we've dealt with these significant point sources, whether it's moisture from showering in a bathroom you want to vent right away, or you're burning your favorite food while you're cooking in the kitchen, we use local exhaust for that. And the question we often have to answer is, so how much ventilation is the right amount? And as I said earlier, we can look at this ASHRAE standard to look at minimum requirements. And for the local exhaust, it's 100 CFM for your kitchen if you're using a range hood, and 50 CFM in a bathroom. And those are not on all the time. That's why I use the word intermittent here. Those are exhaust systems that you control with a switch. So when you're cooking, you turn on the range hood. When you go in the bathroom, you turn on the exhaust fan. And they don't run continuously. You would then turn them off when you left the room, or you finished cooking, or you finished showering. So those are intermittent exhausts that are just those point sources. The whole house approach is to ventilate continuously for all the other stuff because it's emitting all the time. If you're thinking about formaldehyde, for example, is a pollutant people think about a lot. That's emitted all the time from building materials if they're there. Unlike, say, particles from cooking, which are only there intermittently. So for all these other pollutants, we need to ventilate all the time. And the ASHRAE approach uses, it calculates an airflow area, and it's roughly based on the floor area of the home, which for that you can think about that's accounting for all the sort of materials that are in the home, things like carpeting or wood products with formaldehyde in them or what have you. And then another add-on is for the number of occupants. There the idea is that people's activities also generate pollutants, and we need to ventilate for them too. And what's really important here, and why this is really important for high-performance homes, is that after you've calculated how much whole house ventilation you need, there's a credit for infiltration, and that credit scales with envelope leakage. So a very leaky house will get a lot of credit, and you won't have to install a very big fan. And eventually, if your home is leaky enough, no fan at all. But what we're talking about here today is probably the other end of that spectrum, which is for very tight homes, and they get a lot less credit for infiltration than, say, a current standard home. So that's going to be one of the key things we talk about a little bit today, is this idea of how much infiltration you have in a tight home. Usually it's low. One last thing on this is that multifamily homes are treated slightly differently in the ASHRAE standard. You can't get that credit for infiltration. So if you build a very leaky multifamily building, you don't get any credit for that from the infiltration perspective. And the main reason for that is that because in many multifamily buildings, only, say, one of the 6 sides of the building is actually exchanging air with outside. The other surfaces are exchanging air with other apartments, and that way you're getting, say, the odors and moisture and possibly cooking pollutants from other apartments, not from outside, and that really shouldn't count as diluting those pollutants, so there's no credit in multifamily. And typically, the ASHRAE standard sets a minimum rate of something like 1/3 of an air change an hour. This varies a little bit depending on the floor area and the number of occupants, but 1/3 is a typical number. And lastly, there are some special allowances for existing homes. If it's going to be very, very difficult, for example, to install the point source kitchen and bathroom ventilation, say you're in a weatherization program, then there are some allowances that allow you to not do that and increase a little bit the whole house ventilation. So that's sort of background for sort of the minimum things that we do in homes to try and deal with those pollutants. And the question is today, what's different about high performance homes? Because we want to have good indoor air quality in all homes, obviously. But there are some interesting things in particular about high performance homes that brings some interesting perspectives. The first one, as I mentioned earlier, is that new high-performance homes are tighter. The existing housing stock in the country is at about 15 change in hour, 50 pascals. In the 90s, we found this was reduced into the range of about 7 to 10 ACH50, and the natural infiltration you get from that level of leakage is roughly 1/3 of an air change an hour, so roughly like what the ASHRAE minimum standard is. New code homes, are going down to this range of 3 to 5 ACH50, so half as leaky again as they were in the 90s. And high-performance homes are tighter yet. A typical number is somewhere around 2 ACH50, although there are some programs, like if you're familiar with the passive house design standards, they're much, much lower. And they're getting down to 0.6 ACH50, which is really a very, very tight home. And it does take a lot of effort to get from that 2 ACH50 down to the 0.6. It's incrementally harder each step as we go down these bullets to get homes tighter. But if we're here today talking about high performance homes, I think the sort of numbers we want to think about for how tight these homes are is probably less than the code, somewhere in that range of 2 ACH50. So you're probably looking at much, much lower than that 1/3 of an air change an hour we got in our existing homes. And that's not enough. That's why we need this mechanical ventilation as specified in the ASHRAE standard. And A tight home will definitely be underventilated if you rely on natural infiltration. There's no way you'll get enough airflow through the home to dilute pollutants to an acceptable level, whether you're trying to take care of odor, you're concerned about moisture, or the pollutants that are health concerns. And this makes tight homes, and therefore high-performance homes, much more dependent on their mechanical ventilation system. If you're in a very, very tight house, it's essential that a mechanical ventilation system is commissioned, so you're actually getting the airflow that you want, and that it's robust. And by that, I mean 2 years after you've commissioned it, that the airflows are still good. It's possible that there's an argument for not going tighter than, say, 1.5 ACH50. Like, is it essential to get that last ACH50 out of the home? I'm not going to debate that today. It's just a topic to think about when we think about leakage of high-performance homes, is that as you get tighter, you're even more dependent on that mechanical system. A passive house, for example, is going to be absolutely chronically underventilated with no mechanical system. Whereas a new code home, you know, it's not going to be such a problem. And that's important when we talk about, you know, what sort of systems you want to install in a house, because having a system that's incredibly robust and is unlikely to fail then has a lot of value, or rather, although it's more important in a very, very tight house than it is in a typical house. One last thing on tighter envelopes, which is really the key issue here, I think, with high-performance homes, is that people have, I talked earlier about there are particles outdoors that we probably don't want to have indoors. And a tight envelope has got very, very small cracks. And it turns out that if you measure how many particles from outside come inside, we can lose quite a lot in the envelope. And the tighter the envelope is, the more of those particles we lose. And so an added benefit from your tight envelope, you're getting benefits from an energy perspective. But there's also a filtration effect that's getting rid of some of those outdoor particles. There's a slight caveat on that, in that I think there's still some research that needs to be done in that area, looking at different size particles and so on. But it's important to realize that tight homes are not just giving us energy benefits. There are other benefits too, in that we think they're protecting us somewhat from outdoor sources of pollutants. Another positive thing about high-performance homes that makes ventilation and indoor air quality, it gives benefits in those areas too, is that we have a lot less what I call natural draft combustion. Certainly, furnace and water heater backdrafting is a safety issue, and most programs that are involved in house tightening or energy ratings have a consideration for doing safety testing for combustion appliances. But if you're using, say, a high-efficiency sealed combustion furnace or water heater, or you're using a heat pump or electric heat, basically that hazard goes away. This problem we have about backdrafting water heaters and furnaces goes away if the devices don't have that capability and or using electricity. So that sort of reduces the likelihood that we're going to have a problem there. Another way of dealing with it is have that combustion happen outside your super tight envelope. For example, there are attached spaces like attics and garages where, so long as that wall or ceiling between the attic and garage of the house is tight and has very little airflow across it, then we've sort of effectively put that combustion outside. And again, we don't have to worry so much about backdrafting, because those pollutants are not going to end up in the home. However, there is one source of combustion that we do allow in our home, and many people actually preferentially put in their home, which is to use gas for cooking. This is open combustion. All the combustion products go into the house, unless, of course, you have a range hood and you use it. The last point is important. In our surveys that we've done, we find that many people have a range hood, and it would really be helpful if they used it, but it doesn't get used. The usual explanation is that it's too noisy. And we're going to be working on that. I'll talk a little bit more about that later, in terms of trying to get better range hood design and make them quieter, to make them more likely to be used and or make them automatic. But it's important to notice that that these high-performance homes often have a lot less combustion safety hazards because we move the combustion outside and or we don't have it. The exception is cooking, and that's why we want to have range hoods that vent outside. And I want to have a few notes on combustion safety, and this is based on questions that are commonly asked. And a lot of this revolves around high-performance homes that put in what I would call a commercial kitchen exhaust. So these are large, high flows. By high flows, I mean 300 to 400 CFM and up, that are popular in high-end homes. They're exhausting a lot of air. And if you exhaust a lot of air in a tight house, you're likely to have chronic problems with natural draft combustion appliances. And really, you just can't have these large commercial kitchen exhausts and then a water heater in the kitchen that's using its combustion air from the house. You're going to have chronic problems all the time. It's best to simply not do that. Another thing that people like to have in a high-performance home is open fireplaces. By an open fireplace, I mean a fireplace that takes its combustion air directly from the house. You can get sealed combustion fireplaces with nice sealed doors on them that take that combustion air from outside, and they're fine because then you're isolating that combustion from the living space. But this comes up time and time again with a large commercial kitchen exhaust, open fireplace. That fireplace will not vent properly, and really the only answer is don't do this. It's best not to have that. And again, for these large commercial kitchen exhausts, when you're at those high airflow rates, most of the time, a building code and all the manufacturer's instructions will actually require tempered supply air. I would say you absolutely must have it. Even if you're not worried about natural draft combustion appliances or open fireplaces, it's still a really, really good idea to supply some tempered supply air. This is often quite expensive, and so there's a lot of resistance to it, but I think we really have to see these large exhaust systems as part of a system that includes tempered supply air. You can't treat them separately. It will only lead to problems. Now, for what I call regular exhaust, we have much lower exhaust airflow rates, which are more typical, say, a whole house exhaust fan or a smaller kitchen or bathroom fan. We don't have these absolute chronic problems where you're basically designed in failure. But we still need some combustion safety testing. We're in the process of trying to simplify what it means to do combustion safety testing. It's probably still critical, for example, to measure your appliance to see if it's producing any carbon monoxide, both in the living space and in the flue itself, because carbon monoxide is the thing that we're really worried about because it's an instant life safety issue. It's still not a great idea, even if there's no carbon monoxide to vent into the house, because you're filling the house with a lot of moisture, a lot of other combustion products, oxides of nitrogen particles that we have health concerns about. But CO is the one that gets all the headlines. It's the important one, because if it gets high enough, it will actually kill you right there and then. Where these other pollutants have long-term health effects, CO is a very important immediate health effect. So you should always test for CO. And the other test you can do is test for draft to make sure that air is actually flowing up the flue when the device is firing. There's a lot more details to combustion safety testing that I don't have time to get into today, but we still recommend that you do that if you have any combustion appliances in the space with you. It is important to vent kitchens to outside. There's an awful lot of kitchens that have a range hood, but it's just a recirculating range hood. And frankly, they're not worth dealing with. They're not really getting you the benefit because they don't get rid of the moisture or the particles or the pollutants or the odors. You must vent outside to call it effective kitchen ventilation. And lastly, I might have been a little harsh in my don't do it comment here, but in more higher end kitchens, we do see separate cooktops and ovens, where the oven is mounted in a wall or some cabinetry separate from the cooktop. There's often a very nice range hood over the cooktop so that it vents all the combustion products and the odors and the moisture from cooking. But ovens are not vented, and we very rarely see a separate range hood over an oven. In fact, never, right? That just never happens. And we should not discount ovens. Ovens produce a lot more CO than the burners on the cooktop, if you're concerned about CO levels, particularly at startup. They're also producing all the same combustion products we worry about, like water vapor, moisture, and particles, and so on all the time. We want to ventilate that too. And so I see this as a really a problem. If you're looking to have a good indoor air quality in a high-performance home, don't separate the cooktop and the oven. You're creating a very tricky venting system. Now, it's true that you can vent the whole kitchen and try and get rid of these pollutants, but you must ventilate the kitchen at a much higher airflow rate than is required for your range hood, which has energy penalties, can have issues again with combustion safety if you've got appliances in the home that are using the air in the home for combustion, because you're going to depressurize the house a lot more if you have 500 CFM of general kitchen exhaust rather than say 100 CFM through a range hood. So you could ventilate the kitchen that way, but it's not recommended. It's particularly difficult in modern open plan designs where you don't have a kitchen which is a room with 4 walls that defines the kitchen volume. Most modern homes, the kitchen is completely open to the living space, whether it's a family room or a dining room, what have you. And then you have a really big volume that you've got to ventilate, and it becomes even more problematic. And lastly, on combustion safety, as I said, the one thing that doesn't get its own vent in the house is usually the cooktop or the oven. But if you use an induction cooktop, if we're looking at the ultrafine particles that we worry about for health, we get a lot less particles emitted from an induction cooktop, sometimes 50 times less. And the reason for that is it just doesn't get very hot, unlike, say, the flame from a gas oven or the glowing red hot element that you have for a regular electric cooktop. Induction cooktops just operating at a lower temperature. They don't create these ultrafine particles. I should say, though, that if any particles get emitted from the cooking are still there, of course, but the induction cooktop is a good way to reduce the particles that you emit. And admittedly, the most expensive, but again, if you're looking for, if part of your high-performance home includes high-performance indoor air quality, this is something else to consider. Another good thing about high-performance homes is, by and large, they are emitting less pollutants. And this is sort of more of a general new home issue than just high performance, but it's well worth considering. We are putting less formaldehyde in building materials and home contents. And we have seen, in comparing older homes to newer homes here in the state of California, something like a 50% reduction in formaldehyde levels because we are regulating that. And we no longer exceed the California acute standards in new homes. Some harmful chemicals are basically disappearing. We don't see mothballs very much in homes anymore, so we don't see paradichlorobenzene. And just benzene in general is going on. There's a long list of chemicals that are slowly disappearing, but some people say, yes, but there's new ones we're adding that we don't know the health effects of, and that is certainly true. But the ones that we know have solid background information that says this is a health hazard, like benzene, those concentrations are definitely going down in homes because those chemicals are just simply not in the products we're putting in our homes. And just in general, there are lower VOCs we find in homes. And lastly here about formaldehyde, we almost have federal regulations. So hopefully later this year we will actually have this regulation will go into force. Nothing is definite in the world of politics because it has become a political rather than a technical decision at this point. But these reductions that we're seeing in California may go broader nationally if we have some federal regulation of formaldehyde in building products. And I think from the indoor air quality perspective, that can only be a good thing. So I guess what I'm saying here is that this high performance aspect is not just moving air to dilute things. Selecting low emitting materials is a really, really important part of what you do in your high performance home to make it high performance IAQ. You can, as a builder or a contractor or a designer or an architect, you can of course specify low emitting materials for the construction, which is great. We can't always restrict the materials that people bring into homes, so that's still a bit of a challenge. But I think as we are the buildings community, our job is to control what we can control. I think specifying low emitting materials is a fantastic idea. There are many, many lists out there of products that have low emissions. I listed one here, just an example, the Living Building Challenge Red List. You can find your own favorite one and go with it. But again, highly, highly recommended for high performance homes is to use low emitting materials. As I said, there's lots of third party assessment. This is not a complete list by any means, but it sort of gives you some places to start looking. And if you need to prioritize, you want to look at materials that have lots of surface area. I mean, carpets, for example, often have a lot of surface area and have direct passive exposure where people are going to be near these things. And also, it's a little trickier, but often these lists of approved materials will talk a little bit about exactly what the chemicals are there and how they contribute to IAQ issues. So that's sort of the emission side of things and a bit of source control, which is, I would say, essential. We should do it in all high-performance homes, probably in all homes, but in particular high-performance homes, we can go there. I want to talk a little bit now about sort of the three canonical system designs and for providing whole house ventilation. And probably the first one, and the one that we see most in high-performance homes, is a balanced system, mostly because that first bullet. You can do heat recovery through a heat exchanger if you use a balanced system with fans to blow air in and out of the house, and that can be an important part of getting high performance, particularly in harsher climates. However, there's a cost associated with that. You need ducting. There's high-cost equipment. There are less combustion safety issues because we don't have to worry too much about depressurization. And just a little bullet there is that, of course, you have less combustion safety issues if you don't put natural draft combustion in the house with you, which is always the best thing to do. But if you do, a balanced system's not going to impact that too much. You do get the opportunity to filter outdoor air to remove particles, which is a good thing to do. The flip side of that is we have a really big concern with balanced systems about plugged air inlets. We don't have any large-scale definitive survey studies across the nation. We just have lots and lots of anecdotal evidence that it's beyond not unusual to have the air inlet plugged on your balance system, and then basically you've converted it into an exhaust-only system. You lose the opportunity to do heat recovery. You can introduce combustion safety issues that you didn't think you were going to have. So we're thinking about things like maybe we need to start putting an alarm on these systems to use outdoor air. It's just so important to keep that outdoor air coming in for a balanced system, and it's so chronic that they don't do it, that we may have to think about this. A parallel system might be, if you think about your smoke alarm or carbon monoxide alarm, it starts beeping at you when it's about to stop protecting you. Maybe your ventilation system could do that too. If you think about indoor particles, unfortunately with a balanced system, you can filter the outdoor particles, but not the inner ones. So some sort of way of filtering indoor particles is a good idea. Often HRVs are just connected to a central forced air system. If you put a good filter in that central forced air system and run its fan at the same time as the HRV, you can do a really, really good job of filtering for indoor air particles. And I like that idea. I think that's a really good system. Or you could put some standalone filtration in to filter indoor particles. If you don't have a central forced air system, and some high performance homes don't, if you're say running several mini splits in a home and there's no central system, you don't really have this opportunity to filter the indoor particles with a filter on the central forced air. So you need some sort of standalone filtration. Another thing is more of a controls thing that we've seen in some high performance homes where particularly passive homes, which are very, very tight, where they have concerns about, can we actually get enough airflow to our kitchen range hood when we turn it on because our house is so tight. And a good idea is that you could interlock the operation of the kitchen exhaust with your HRV with some dampers, so the HRV goes in supply-only mode for when you're cooking to balance that out. That seems to be a pretty good idea. Mostly that's going to apply only to very, very tight homes. The second system I want to talk about here is about supply systems. And although the illustration here shows it connected to a central forced air system, there are standalone ways to do this. And in humid and cooling dominated climates, this is often a good idea because you pressurize the home slightly, and this stops humid outdoor air coming in through the envelope, contacting cold surfaces, and then you have condensation and moisture problems in the actual building structure itself. And if you have a supply system and pressurize a little bit, I'm not going to say you're going to remove those problems, but you're certainly going to minimize them, and that's why we see supply systems in those climates. Really good idea. again, if you're going to have combustion things in the house with you, you're going to have less combustion safety issues with a supply system that slightly pressurizes rather than depressurizes the home. Like with the balance system, you have this opportunity to filter the particles in the outdoor air. However, you do need some sort of tempering. Either you connect to a central HRV, or you've got to mix with some indoor air. And this is something which has two sides to it. This means you're going to need more ducting, more fan power. But this idea of tempering this indoor air with a fan and some ducts means that, again, you have the opportunity for also filtering the indoor air as well as the outdoor particles. So this we really like this idea of filtering. But just like the HRV system, a big concern is plugged air inlets, because once the air inlet is plugged here, there's no ventilation going on. Unlike the balance system, at least it's still an exhaust if the air inlet is plugged. For a dedicated supply, you better make sure that air inlet stays open all the time. And the last of the three canonical systems is the one that is probably seen the most, and this is an exhaust system. I think it's popular because it's simple and it's cheap. For example, you could put a bath fan in there. It's a double-duty bath fan that operates on a low speed for whole house ventilation. Then you can put it into boost mode. We see that quite a lot. There's no tempering of the air required. Basically, the tempering happens as the air comes into the building envelope. Of course, the big downside that we touched on earlier is that if you have combustion appliances in the space with you, it can be a combustion safety concern. So there's extra testing you probably have to do to your home if you use this system, and that testing becomes more important as the house gets tighter, as high-performance homes tend to be. Unlike the other systems, we have much less opportunity to filter other particles, although we have some data that says the tight envelopes can be a pretty good filter for particles. It is more robust mostly because we don't have to worry about an air inlet plugging up. And like the supply system, you need another system to filter the indoor air particles. You could, if you have a central forced air system, you could put it on a timer and install a good filter and just have it operate totally separately from the exhaust in order to clean the indoor air. And that's probably a good idea for an exhaust-only system. And I talked in those three systems about filtration. And why did I talk about it so much? Really, this is a health issue. Particles are the most important pollutant in homes for health. They're in almost all homes. They're ubiquitous. They're at levels that are a concern. And it's a really, really good idea to remove them. Now, the ASHRAE minimum standard, 62.2, it requires a filter and a central forced air system. But it's only a MERV6 filter. That's not going to remove the particles of concern for health. But you should know that it is, in fact, being considered, whether it's as an actual requirement that you filter air. I don't think we're ready to go there yet for a host of reasons. But it's going to appear likely as a credit. In other words, if you have a central system recirculating air through a good filter, probably in the MERV 13 range, you won't need so much whole house ventilation because we believe that you are having such a positive health impact by removing all those particles. A kitchen range hood, by the way, is a great way of reducing the indoor particles from cooking. So again, I'm going to hammer on this. Install a range hood that vents to outside and use it. It must turn on because cooking is by far the most important indoor source. There are other sources, like if you have incense or candles burning, obviously, you're going to put a lot of particles in the air. And just to sort of fill out a little more about this ASHRAE credit, I did a quick back of the envelope calculation for this credit. This is currently not part of the standard, but it's likely to be coming up soon. Is that you only need to move something like 150 to 200 CFM of recirculating filtered air in the standard to get the credit. So that, just going to the bullets at the bottom of the page here, because you don't need the much higher airflow that you would normally have for a heating and cooling system, this means you can maybe take your central forced air heating and cooling system, only operate it periodically, or if you install a very good variable speed blower, you can operate at the lowest speed, and that gives you very big benefits in terms of reducing the fan power requirements in order to do this filtration. And I've seen systems that if you're running them down in that 150 to 200 CFM range, with a well-designed low-pressure drop duct system, you're looking at maybe only something like 25 watts continuously to provide this filtered air. Now, people might say, yes, but I'm building a high-performance home. I need to reduce the power as much as possible. But so I guess this is an option. I'm not going to say it's a requirement, but it's something to think about. You're definitely going to see a good indoor air quality improvement by removing the particles. The question is whether or not you think that 25 watts is too much or too little is something that I won't answer here, but it's something, you know, one can debate. So what about installation and durability issues? The reason why I say this is that it's no good just to simply install a system. It absolutely has to work. And as I mentioned earlier, in homes with super tight envelopes that can't rely on natural infiltration, it really, really absolutely has to work. So we need to verify airflows. We need to get airflow measuring devices and go and measure them. And that sounds like, well, that should be pretty trivial, right? You buy the right piece of equipment and you spend a few minutes in each house verifying you get the right airflow. It turns out it's not so easy. Kitchen range hoods could be quite tricky to measure the airflow of. It's kind of hard to get underneath the range hood and have something that captures the flow there, particularly as some range hoods suck air not just from directly above the cooking surface, but also in from the kitchen in the top of the sides. Particularly, I'm thinking of microwave range hoods. They have several air inlets, and it's hard to measure them all at once. You could say, well, then find where the outlet is and go measure that. That can be inaccessible or hard to access if it's on a roof and so on. So I think we need some better ways of measuring kitchen range hood airflow. It can also be tricky for supply systems. Again, a lot of it has got to do with how do you get access to the actual duct that has the airflow in it. The inlet might be on a roof or higher on a wall, making it hard to get to. On the inlet side, if it's connected to a central forced air system, it's coming into a return plenum, places that can be hard to access. And for both these kitchen and supply, and I think guess what's the next, but the HRVs, there are some manufacturers that are thinking about building in a little flow meter, or at least access to install a calibrated flow station, which I think is great. We're not there yet. It's kind of rare, but I highly, highly encourage that. Another tricky thing for HRVs is that they tend to have very, very low airflows per inlet and outlet, and a lot of devices on the market for measuring airflows are very poor at these low airflow flows, and that makes it tricky to measure and verify. And the last thing on HRVs is when they're actually installed and connected, there's usually 4 connections on an HRV. You've got fresh air from outside that then gets supplied to the house. That's an inlet and an outlet. Then you've got the return from the house that then gets exhausted outside, so another inlet and an outlet. And sadly, it's relatively common to see those connections switched. So it's not just enough to verify that you've got the right airflows in HRV. You better go to that HRV unit and make sure that the ducts are actually going where you think that they are going. Again, there are issues with clogged inlets and filters, and I have a relatively graphic image here, but this is what we see on intake hoods. These are critical for supply and balance systems. This is a durability issue. If you can trust people to clean them, that would be great, but we think that's not possible. And I think in the future, we're going to look to maybe having some sort of alarm system or some automated system that tries to take care of that. And typical surveys also been done in the US and Canada and a few other places looking at several hundred supply and HRV systems. Shows that roughly half of them are not working properly. A combination of the incorrect connections, they never verified the airflow to make sure they work properly, clogged inlets and filters, and half not working properly is far too many. It's really an issue our industry is going to have to try and deal with, and we're not there yet. I think there's some positive things coming along. I think as more of these devices get installed and installers get used to it, they will definitely get better at it. I think this idea of verifying airflows is getting more traction, and we'll do that more and more simply because we're getting more and more interested in verifying home performance in general, and this is just another aspect of that. What to do about inlets and filters? I think eventually we're going to have some sort of alarm system. A last point on this for installers and designers is it would be great if you could get to all the HRV or supply inlets and outlets, I showed a few examples of things here which are incredibly difficult to get a measurement device over, meaning that how do you verify you've installed things properly? Almost impossible for some of these things. And that's sort of a design and installation issue where we need to get away from the idea of if you hide an air inlet far up in a corner and put it next to a light fixture that you'll ever be able to verify its airflow, because you won't. And so when we're designing and installing these things, we also need to think about where we place our inlets and outlets so we can actually make sure that these things are operating properly. So I'd like to summarize now a little bit about, so given all this information about different systems and their performance and the caveats and what to look for, what might be some recommended ways to ventilate your high-performance home? And I think we can always agree that you should exhaust from your kitchens and the bathrooms. They are high sources of pollutants, and we should exhaust from them. That's by far the most efficient way to do it. You need to install a range hood and use it. There are some automated range hoods on the market, but very few. And most of the automation is safety-based and only operates at very, very high temperatures. And so the range hood industry is not, you can't go out there and buy a whole bunch of automatic range hoods. But we think this is coming. And a few years from now, I think there'll be a lot more automatic range hoods around that as soon as you turn on the burner, that there's a switch happening there. That switch will be integrated to the range hood and will turn it on. If you must put in a really big range hood with, say, more than 400 CFM exhaust, one of these commercial style range hoods, you've got to install the whole system and install the tempered makeup air that goes with that. You can't just simply install that thing and expect it to work and expect it not to have any impacts on the home. I would really, really like there to be no natural draft combustion inside the home. So either it's sealed or you put it outside your tight envelope. From the whole house perspective, probably most high-performance homes are going to be pretty tight. They're going to be close to this limit I put there. And particularly in cold climates, you should almost always use an HRV. It's going to be great from a thermal efficiency point of view. It's balanced, so even if you do put, say, a water heater in a kitchen, it's unlikely to backdraft it. And if possible, integrate that into the central forced air system so you can add some sort of filtration. And these are just sort of standard HRV installation ideas. You would then supply to bedrooms and living rooms, exhaust from kitchens, bathrooms, and laundry rooms. So you exhaust from the places that you think are going to be more polluted than others. And you supply to places that you think people are going to be in. And I think that for very tight homes, say less than 1.5 ACH50, that don't have a central forced air system for heating and cooling, supplying to the bedrooms and living rooms, I think, becomes even more critical. And so a lot of high-performance homes are going to fall into that category. Again, super tight, no central forced air system to make that supplying to bedrooms a good idea. Things like, I emphasize that the 62.2 airflow rates, which people often use as a reference, they're the worst you can do. That's the least airflow you should have. And so I think it's nice to build in a bit of extra capacity to your system. So you can add a boost mode for high occupancy if you're having a party or something, if your range hood isn't working, or just if there's an event that creates some sort of odor in the house you don't like, or you've burnt the toast and there's been some cooking failure. It would be super nice to have for any of these systems, whether it's HRV, supply, or exhaust, a button that you push that would say double the airflow rate for 20 minutes. You put it on a timer and it turns off again. That's a really good idea, particularly when we're talking about super tight homes that don't have much natural infiltration. If you put 20 people in it because you're having a party instead of the 4 people that we set the minimum rate for, you're going to want some extra ventilation. And boy, we need to find ways to make these systems more durable. And I think probably trying to figure out a way to have alarms is a really, really good idea. If your house is not down in the less than 1.5 ACH50 area, some things become, I think, a little less critical. I don't think you need to have a balanced system. And maybe here, I think there's some climate dependence. In a cold climate, an exhaust system is probably a good idea, whereas in a hot humid climate, you need a supply system. That difference is mostly got to do with moisture issues in walls and the direction of the airflow and where the moisture is. So I think we do need to distinguish between the climates when we're trying to pick between exhaust and supply. And again, the supply offers this opportunity for, you're going to need a tempered system and you could attach it to a good filter. But independent of all the climates and envelope tightnesses, if you're talking about health impacts, adding some sort of filtration, something like MERV 13 and up, but MERV 13 is a good place to start. That's going to have probably the biggest health impact, and it's highly recommended, independent of these other systems. I'd like to talk about multifamily for a minute. As I said earlier, there's no credit in 62.2 for multifamily, which means that if you build a tight multifamily building and a loose multifamily building, they're going to have the same requirements. Fair enough. And that's because we don't want to be mixing pollutants between apartments. And a key thing there is this thing I call compartmentalization. So there I'm not talking about the air leakage to outside for a dwelling unit or an apartment. This is the air leakage to other parts of the building, whether it's corridors, it's your neighbors above you or to each side of you. And currently in 62.2, we do have a specification. And the idea is that you would do a pressurization or depressurization test, measure the airflow at 50 pascals, and for every square foot of the envelope area, and that's all to sides, not just the bit that's to outside, there's a limit of 0.3 CFM. So if you have a 500 square foot of envelope area, sorry, 1,000, let's do it, it's easier for me if it is 1,000 square foot of envelope area, then you move that distance point over, and 300 CFM at 50 pascals is the tightness limit. This used to be tighter, it was 0.2, but an issue came up about people thought we could not meet that. I think we need to discuss this a lot more. You know, is the 0.3 or even the 0.2, are those really good enough to say that we're not going to get pollutants mixing from adjacent apartments? Obviously, we have to temper this with, you know, what can we reasonably achieve in construction? And the tighter the better, and what the limit is I think currently something that our, you know, the building community, we need to debate that. I think you probably need to get tighter. The examples I think of are the ones that we see and hear complaints about are often odors from cooking, and the number one thing is cigarette smoke from adjacent units, and how we limit that. Sometimes people have gone to no smoking buildings, which helps, but many buildings are not going to be non-smoking, and eliminating cigarette odor transport from apartment to apartment is probably going to need better compartmentalization than this, but that requires, you know, a lot more careful design and require, I think, a lot of effort in multifamily buildings. But if you're building a high-performance multifamily building, I think good compartmentalization is definitely part of calling that a high-performance unit. In terms of whole house kitchen and bathroom exhaust, whole house ventilation, kitchen bathroom exhaust, it's basically the same as single family. The requirements are the same. Normally the airflows will be smaller because each unit is smaller, and it's done on a unit by unit basis. So, you know, we talk about smaller fans, less airflow, but generally the whole house thing is the same. The kitchen and bath exhaust are the same airflow, like the whole house, as a single family. In other words, you still need 100 CFM in your range hood or 50 CFM from the bathroom. Again, with very, very tight units, probably adding a balanced system is a good idea because of opportunities for heat recovery, opportunities for filtration, and so on. And again, there's probably some climate-related issues similar to single family because of moisture considerations, whether you want to exhaust in cold climates or supply in hot, humid climates. Those issues of transporting moist air through the building envelope are going to be the same in a multifamily building as they are in a single-family building. One additional thing about multifamily is that there's probably a lot more options available. You know, a single fan serving multiple units, it's ducted with dampers in it and so on, is something that obviously you would not do in a single family, but in a multifamily you have the opportunity to gang systems together and have designs that might, you know, optimize in terms of using less fan power, for example, because you're going to have one single very efficient fan that serves multiple units. We have to be a little bit careful about how we damper those and, you know, prevent airflows from apartment to apartment, but that's all doable. Or we can have individual small systems, just like in a single family. A lot of that's going to depend on how the multifamily building is constructed, the construction methods that are used. Is it high-rise? Is it low-rise? Are going to determine those. And then you get into some, particularly if you're doing, single-family communities, you get into some fairly sophisticated design that is a little bit more like commercial building ventilation design. And to finish up here, I want to look a little bit to the future of how we're probably going to ventilate our lovely high-performance homes. The first thing I want to talk about is something that we call smart ventilation, which has at its core this concept of time shifting. So changing when you ventilate. And a key thing here is if you're going to change the ventilation rate with time, we still need to make sure that if you have the same emissions in a home, that you're exposed the same as a continuous system. But there are calculation methods to do that. And what we want to do is things like, if we move the time that we ventilate from times of high temperature difference to low temperature difference, and still maintain that same exposure, we can definitely reduce building loads. We can reduce energy use. I suppose the classical application here would be if it's winter, it's cold outside, you would ventilate less for, say, 4 hours just before dawn when it's coldest, ventilate more in the afternoon when it's much less cold. And so, your total for the day is the same, you get the same exposure, but we've reduced our energy costs to do that. Another one is if a home is unoccupied, you could reduce ventilation when it's unoccupied because people are not there to breathe the pollutants. There are some caveats involved with that, in that there's probably a minimum ventilation we don't want to go below, because you don't want to come home at the end of the day, open the door to a tight home that wasn't ventilated, that now has very high levels of pollutants in it. You don't want to exceed acute levels of pollutants that would have some sort of instantaneous health impact on you. So there's some caveats there. So that's why I didn't say go to zero ventilation when unoccupied. We probably still have to ventilate a bit, just so that we don't have very, very high peak concentrations you get exposed to when you first re-enter the space. Another thing to do is to be more responsive to outdoor pollutants. You can get off the web information that's local for outdoor particle and ozone level. And you could have a ventilation system that was able to use that information off the web, ventilate less at times of high particle or ozone levels, ventilate more the rest of the time. High particle and ozone levels tend to be periodic rather than high for extended periods of time, unless you're in the middle of a forest fire or something. And that means that we can use this time-shifting idea to, let's say, ventilate less during the morning commute if you live next to a freeway, but ventilate more at night when there's a lot less traffic on the freeway and particle levels are lower. And so we can reduce our exposure to pollutants simply by time shifting. From a utility perspective, we could use our ventilation system to respond to peak demand. So we could turn off or reduce our ventilation during, say, the late afternoon in climates that have a lot of air conditioning, like here in California, ventilate more the rest of the time. So again, the key thing is that you need to still maintain the same exposure by ventilating more other times, but we could reduce the ventilation contribution to peak loads in homes by time shifting to reduce peak demand. For most implementations of this, you need to, the smart bit is that you need to track when your ventilation system is operated and what its airflow was when it operated, and do a calculation of what the exposure is to be able to control your whole house ventilation system. But the algorithms for that are relatively simple. The computing requirements are low, and it's getting pretty low cost to put this sort of control strategy into ventilation systems and fan controllers. And lastly, if you were to put this fantastic smart ventilation system that maybe saves 40% of your ventilation-rated heating loads in the winter, you surely would like to get some sort of a credit for that, whether you're doing a home energy rating or if you have a state energy code or local energy code you want to comply with. And so we do need some effort to get standards to recognize some of these advantages of smart systems. They're not there yet, but I know from the ASHE 62.2 perspective, we're certainly working on that. so that you'll be able to get credit, at least from the IQ perspective, and hopefully, if we can change energy codes from the energy perspective, for doing some of these smarter things with related to ventilation. I think these are particularly effective in high-performance homes. When we think about how little building load there is from the envelope, because we've got lots of insulation and really good windows, the fraction of the building load that is due to ventilation is going to be much higher in a high-performance home than a regular home. So this ability to time shift and maybe save some of that, I think, is a really good tie-in to how we want high-performance homes to work. Some other things we want to do is for range hoods, we want to get away from specifying an airflow rate to specifying what I call here capture efficiency. What capture efficiency means is if some pollutant is emitted on the cooktop, what fraction of that pollutant is going to go straight outside because it gets sucked out by the range hood, what fraction of it goes into the kitchen and mixes and is there for you to breathe. And we've tested quite a lot of range hoods in recent years, and this capture efficiency number has a huge range. Some range hoods are very good and capture a lot of the cooking pollutants right away. Some range hoods are not very good. And it's all related to the actual physical size of the range hood. Does it fully cover the cooktop? It's related to the actual physical dimensions of the cooktop. Does it have a plenum that captures the plume, the hot plume that comes off the cooking? And we're currently working on an ASTM test method for capture efficiency that will allow the manufacturers of range hoods to label their products with a capture efficiency. And it will allow standards like mechanical codes or ASHRAE 62.2 or what have you to say, you know, we want to have a minimum capture efficiency level for the range hoods that you install. The reason why we like capture efficiency better than airflow is it's actually affecting the thing we care about, which is how much pollutants enter the space, and also because it allows us to do some clever designs where if you have a very well designed range hood, maybe we can have good capture but lower airflow. And lower airflow will mean less noise, and we know anecdotally that noise is the reason why people don't use their range hoods, so we're likely to get more range hood operation. We need less fan power. The lower airflow means we'll have a lot less impact on combustion safety issues. So a high capture efficiency, low flow, low noise range hood, I think is coming in the future. And these range hoods, because they don't work if you don't turn them on, they probably need to be automatic. Current sensors are doing things like sensing the temperature above the stove, but I think we probably want to move to things that are fully integrated with the controls of your cooktop or your oven, so that when you turn the knob to turn on the gas burner or the electric burner, the range hood is connected to that signal and it turns on. Even if it's just at some sort of low minimum speed, I think that would be a great step forward. This idea that it's kind of tricky sometimes to measure the airflows for verification means that it would be nice to have some sort of more automatic systems. And indeed, there are some HRVs out there that have flow stations in them and might be able to do some sort of self-calibration. And what we'd like to do, if you want to simplify it, is there could simply be a button that says push to test that an HRV installer, after he's done, can push it, and he either gets a red light or a green light or a series of red lights that say, the problem is here or there. This sort of automatic verification, I think, would be a super duper idea, and probably some sort of continuous monitoring, particularly I think for supplying systems or for filtration systems in general. There's some sort of alarm that tells you to change the filter. Particularly as we think more about particles and filtering them, that's going to become more important. But simply to make anything that supplies air robust, that's probably a really good idea. I think we're going to do more filtration in homes for sure, mostly because particles are the #1 health issue. Possibly we'll look at gas phase removal, so that means removing things like possibly formaldehyde, maybe some other VOCs, oxides of nitrogen, and so on. But I think the gas phase stuff is far into the future. But in the near future, I think we will be doing a lot more particle removal. Another thing is that I probably think most of you on the call are familiar with getting an energy score for your home. And there's several energy scoring systems out there. And I think what we need in order to reap the benefits of building this high-performance home and putting in really good ventilation and filtration systems is some sort of a scoring system that reflects that, so that you folks who are doing the right thing can be recognized for what you're doing. And you know, something that will account for smart systems, whether or not you verified the flow, what sort of filters you've installed, do you have, you know, an automatic range hood, and so on. I think that we need some sort of scoring mechanism that will be sort of analogous to these energy scores that we have, where you require something sort of simple observation, you know, does a fan exist in this home? And then, you know, some diagnostics for airflow, which is kind of what we do right now for getting an energy score. We'll often use a blower door to figure out the house leakage. Well, maybe we'll measure some airflows in our ventilation system, so there'll be a measurement component of the score and an observation component of the score. I really like that idea because a chronic problem with identifying indoor air quality and selling indoor air quality and so on is most of what we're talking about here is invisible, particularly the health-related aspects of it are things that people do not detect. And so it's a very intangible thing for most occupants. But getting some sort of a score, I think, might help us along there. And we're currently at LBL starting up some of that work. We're working with Building America, and so some of the other national labs are going to contribute a bit, some of the teams, and we're trying to sort of put together people's ideas right now. We're just at the very, very beginning of this, trying to figure out what metrics look like and how do you compare the health impact of a filter versus more whole house ventilation. All those complications are still being worked out. But I think from the perspective of high-performance homes, high performance has got to include not just energy, but indoor air quality. And we need to recognize that in the same way that we do by scoring homes for high energy performance. We need to score them for high indoor air quality performance. And I think I will wrap up with my basic presentation here for now. And we're going to have some Q&A. But if you think of things afterwards, you can see here my contact number, my email and phone number. And if you want to know a little bit more about the group that I work in at LBL, you can go to homes.lbl.gov, where there's quite a lot of resources and a bunch of background information on a lot of the things I've talked about here. A lot of our research is available online in various reports and so on.
Great. Thank you so much, Ian. I wanted to also thank the participants who've submitted questions, and we have way too many for you to answer in the time that we have left. So I'm going to start, and we'll get through as many as we can. Sound good?
Okay. Yes, go ahead.
Okay. So the first question I have for you, if a tight home has a balanced ventilation system, shouldn't supply air dynamically balance exhaust depressurization?
I'm not exactly sure what the question is there. Yes, if you could have separate supply and exhaust fans, but not have an HRV installation. If that's the question, that's for sure. Or you can think about the situation where if you have a supply that's operating continuously, when you turn on a bathroom exhaust fan or a kitchen exhaust fan, if it's of a similar airflow, and they will be for most homes, basically you're going from supply to balanced when you do that. That is certainly true.
Okay, the next question, is there an industry standard ASTM blower door test method for multifamily homes?
Oh, that's a good loaded question. Well, there's probably most of you on the call are familiar with the ASTM E779, which is really applied for single family only. And there are various protocols out there that various institutions have put together. There is no sort of ASTM or ISO standardized test method that deals with multifamily. And it is a tricky issue because from an energy perspective, you often want to simply isolate the air leakage to outside. So pressurizing just one apartment isn't helpful. You need to pressurize all the other apartments around it. And more than that, because there's often lots of interstitial spaces that are linked to other parts of the building, even that doesn't work. It's an incredibly difficult thing to isolate that air leakage to outside for an individual unit. And it could certainly, we can do better by also pressurizing adjacent units. And if you've got, say, a row of townhomes, it does get a little more straightforward in that now you don't have 5 extra faces, you only have 2. And there are definitely good protocols for testing row houses where you do blower tests on all 3 simultaneously. You sort of do what we call a guarded test. That's doable, but in more multifamily or high-rise, it does get increasingly difficult. I will say, however, that the solution to that might be that we think these buildings should be tight to outside and also tight to their neighbors, and probably very tight if we're thinking about airflow between units. And so some sort of leakage specification like the one I gave for compartmentalization, we're going to have super low target numbers. And that's going to minimize, and so we're simply going to test the whole unit, get the leakage through all of the faces of the unit. If that is super low, the amount of leakage through the external part is even lower than that. It lets us certainly put an upper bound on that airflow we might get through the external face from an energy perspective. But that's probably where we're going to end up, and at which point maybe those airflows to the external envelope are going to be so small that we don't care about them. Maybe not. It's going to depend on that compartmentalization criteria. But unfortunately, we just don't have a super duper always works great method for air leakage testing in multifamily units to outside. There are some people who've done great work in this area and have done good testing, but there isn't some sort of standardized test method that people can go and say, yeah, this is always going to work.
Okay, the next question is, please explain why you wouldn't recommend makeup air for kitchen exhausts less than 400 CFM in tight homes.
Well, I think the main reason for that is that why would I care? If I don't have any combustion happening, so I'm not worried about backdrafting, for example, a little bit of depressurization of a home doesn't really hurt anything, so I'm not too concerned about turning on a range hood. It doesn't hurt the occupants, doesn't hurt the structure. It's not on all the time, right? It's only on while you're cooking or while you're in the bathroom. And so I don't think for a typical, let's say, 100 CFM range hood that you need to provide makeup air in that situation, unless you're living in a welded stainless steel box. Even a passive house down at 0.6 ACH50 probably does not need to have any makeup air that's supplied for the kitchen exhaust. I do like the idea, however, of having a control system in a very, very tight house that switches to supply mode only when you turn on the kitchen exhaust. For quite a few reasons. It keeps the home balanced for start if you care about that, but also there may be issues in a very tight home. If you don't have a very good blower mounted in the kitchen exhaust, you might not get the airflow that you want, and you might not get the exhaust of the kitchen pollutants you want, in which case balancing that out with a control system that makes the HRV go to supply only would be an assistance to make sure you do get the flow that you want through the kitchen range hood. But otherwise, at the lower airflows, particularly once you've taken the combustion appliances out, a little bit of depressurization is not an issue.
Okay, great. The next question, in climate zone 3, mixed humid, what would you recommend for dehumidifying the whole house makeup air, short of having to add an ERV?
Yeah, I think that if your concern is about humidity control, an ERV can help in the sense that if you've put in a dehumidifier and actively are dehumidifying a home much below the outdoor humidity, the ERV will certainly mean that that dehumidifier has to run less. But the ERV on its own is not going to be enough to control humidity in your home. You're going to have some sort of deliberate dehumidification system, that's whether it's part of your air conditioner or just a standalone unit. You're going to have to actively dehumidify, and if you want to do that, from an energy and efficiency point of view, it's often better if it's much more humid outside than inside, to dehumidify that incoming airstream, simply because if you're using a vapor compression system and some reheat, which is what most of these systems are going to be like, they're going to have a much higher latent to sensible ratio at higher air humidity content. And so they become effectively more efficient dehumidifiers as the humidity content of the air goes up. So you would like to dehumidify that incoming airstream when the outdoor air is more humid. If you want to get really advanced with your dehumidification, you could install a damper and maybe have an indoor and an outdoor sensor and switch which airstream you were dehumidifying, depending on which one has the most humidity in it. But again, then you're adding complexity of controls and sensors you have to make sure work in dampers. But, you could really eke out some more efficiency there. But if you are going to dehumidify and you've got a supply air system, then it actually is a good idea to actively dehumidify that air that you are supplying rather than the air in the house through some sort of internal mixing or what have you.
Okay, the next question is, do you see air quality sensors being installed tied to ventilation systems in the future?
Well, the future is a long way away, or it's tomorrow. And the short answer is tomorrow, no. In the near term, we're a long way away from sensors that are either cheap enough or robust enough. And I think the robust part is the key thing here. Certainly, some sensors have come down in price to the point where you could reasonably consider adding it to your home HVAC system. But whether or not they're doing the right thing 5 years from now is certainly problematic and almost certainly not the case. If we're talking, say, 10 years from now, it's possible there will be some breakthroughs. I know that there's a huge, huge amount of activity in this area developing sensors for pollutants. But they currently aren't there yet and won't be for a little while, at least at the commercial level. There are people who are trying to bring costs down doing, say, open source stuff, so that if you're an equipment designer or specifier, you could use some of those resources. But again, they are limited by the fact that these sensors they don't hold their calibration long enough, or they don't work well enough for long enough for us to rely on that as controlling our ventilation system, rather than what we do now, which is this outdoor air to dilute. I mean, the theory sounds great, right? The theory is that, well, if you have a bunch of really, really good detectors that tell you, oh, there's almost no pollutants in the house today, so you don't need very much ventilation, you can see why that's attractive, right? You can see some significant energy benefits there. And the other side of that coin is, if they see that pollutants are high, they could go, oh, we better turn up the ventilation a lot right now, and then you can see the IQ benefits. That's an ideal. We're just a long way from it, and it's mostly due to cost, and the sensors simply are not robust and reliable enough to be used in that way yet.
Okay, another question for you, Ian, is have you considered using dry bulb temps in the ducts, calculating effectiveness, and using that to determine when filter needs change?
Oh, this is talking about some sort of way of knowing when you should change your filter.
Mm-hmm.
I think what's being talked about here is as a filter gets clogged, its airflow resistance goes up. And if you don't have a very good blower in your heating and cooling system, as the airflow resistance goes up, the airflow goes down. You expect then to either be delivering hotter air from a heating system or cooler air from a cooling system. And if you had a temperature sensor that carefully tracked that with time, you could maybe detect, oh, I'm delivering air slightly colder now from my air conditioner, and say that corresponds to a certain change in airflow, which corresponds to the filter being clogged, and say, it's time to change the filter. I think that's possible, but unfortunately, more high-performance heating and cooling systems tend to have blowers that don't change their speed with increasing flow resistance. They just work a little harder. And so that signal is not really available to us in high-performance equipment. It's ironic, I suppose, that if you installed, equipment that meets only minimum efficiency standards and is not particularly high performance, you might actually have a signal you could respond to. So it's theoretically possible. I think it's a little tricky, but I'm sure it's doable. But again, I think we're sort of this is a bit of a catch-22 here. We want to install really good high-performance heating and cooling systems in our high-performance homes, and unfortunately, those are the systems that have the blowers that don't respond very much to airflow resistance. So it's hard to find a way to make this temperature change be the sensor. I think if we are going to sense something about filters, I think it's going to have something to do with some way of a really inexpensive way of sensing the pressure drop across the filter itself that's independent of airflow rates and temperatures for these very reasons, because a modern piece of equipment with a modern blower in it, it doesn't change its airflow. I know that some people have speculated about, okay, so you've got this fancy blower that maintains the airflow, but we know that its control is therefore changing, right, as the airflow resistance of the system changes. And maybe we could detect that and infer that the airflow resistance of the system has changed from, blower motor power signatures and things like that. That's certainly possible, but that's getting pretty esoteric, but it's not beyond the realms of possibility. I genuinely think we'll find some way to actually measure the pressure up across the filter itself. I mean, these things have been around before. There have been some basic, simple, what I would call your basic fluid mechanics system, which is simple whistles that once the filter gets plugged up, you get more filter bypass. And if you put a whistle on there, you reach a point where you've got enough airflow through the whistle that actually makes a whistling noise. Those have existed for many, many years. Or you could have a simple, maybe a simple manometer and a simple electric circuit to turn on a little red warning light that would be robust and would last for 20 years without any maintenance and so on. So I think a simpler approach is going to be better because it's more robust. And I think we're going to probably actually sense the pressure drop across the filter itself because it's more of a direct indicator, if you will, of the actual filter performance. And some of these things have been around for 50 years. We just don't use them very much right now. And maybe they're going to come back. We'll see.
Okay, we're going to see if we can get through a couple more questions before we do our quiz. But the next question is, what is the origin of the 0.2 CFM per square feet envelope area tightness metric for multifamily homes?
The origin of that is that some very tight multifamily homes were built and got tested, and that was roughly how tight they could get them. So it's based on people going out and measuring this in the field. Now, the caveat is, by no means were thousands and thousands of buildings tested, and we didn't have there wasn't a program of how much would it cost to get any better or what have you. But the basic number comes from people built some the best they could do, and that was sort of felt as the best they could do because they went and measured it. So it's not based on some optimum of how much the energy use will change, or some optimum based on what we think the pressure differences are between apartments and the maximum flow we could get or we would allow that would allow for smoke transport. It's kind of based on what people could actually do in the field. And so this is why I say I don't think that's a settled number. That's a debatable number. We might think that particularly, I think tobacco smoke is going to be the number one because people are actually getting sued for transport of tobacco smoke between apartments, and that gets people's attention. That we may have to go to a tight spec. Then the question is, what are the construction techniques we need, and can we do it? And then some people would have to go and do some more blow door testing and see how good we can get. But the basic answer is it's based on some field testing of a few apartments that were tight, and it's no more complex than that. And clearly, I think some more thought and work is needed to finalize that number. And I put it there as I would call it more of a place marker than this is absolutely the right answer. I'd love to know what that number should be better than we do, but it's sort of the best we know based on other experts that have gone out and measured air tightness of apartments. And some of those people who did that work are on the 62.2 committee by the way. They're actively involved in writing the standard. But as an industry, I think boy, would we like to know better what that number should be, both from the perspective of how low does it need to be to stop pollutant transport, and how good can we reasonably expect construction to get.
Okay, let's go through. This will be the last question for you, Ian. Is
Okay.
there data showing the health issues with inadequate ventilation?
There's all sorts of stuff out there. There's a lot of epidemiological studies, but very few of them, unfortunately, answer some of our more very specific questions. Like, if I add 25 CFM ventilation to homes, how much does health change? Those very specific answers, we simply don't know. What we do know is what levels of pollutants are of concern from a health perspective, and what ventilation rates are needed to control those to within reasonable levels. Again, this is actually a bit like the previous question, in that there's a lot of work on the health side, but in my mind, probably not. We haven't really done enough measurements in homes. I'd love to do more, but the measurements we have done show that we need to have, in order to keep, say, formaldehyde levels below a certain point, based on standards, or particle levels below a certain point, or what have you. The ventilation, these are the ventilation rates. We need to control them. Of course, if you ventilated more, you could make them lower and be further away from the health risk. And health risk is never an absolute, right? They're population based. Sometimes they take the midpoint, sometimes it's the 80th percentile. If you're trying to protect sensitive populations, say asthmatics, then you need much lower levels of pollutants, and the effluent rates we're talking about are clearly going to be inadequate. But from a minimum perspective, or for what you want to use in a typical home, we probably don't want to go that far. So the answer, unfortunately, is very squishy, right? Because the range of health effects is large on people for the same amount of pollutant in the space. But we're sort of doing the best we can. We look at what the health community says about, here are some standards for what level of pollutants are acceptable, and then we measure pollutants in homes, or we think about emission rates and trying to what airflow rate is about right to make sure these levels don't get too high in most homes most of the time. So it's not all homes all the time. It's not sensitive populations. So it's not, we have a fixed number, but it's not the answer all of the time. But it basically comes from large-scale epidemiological studies that look at the health effects of various chemicals or particles or what have you, and then what ventilation rates do we need to maintain those levels in the home. And as I pointed out sort of early on in our conversation here, if we emit a lot less in the home because we only bring in materials that don't emit, then maybe there's a case there for saying, well, you could ventilate less in the house, right? Conversely, of course, if we emit a lot, the opposite is true. And the other bits of evidence we have tend to be, we don't have the large scale, changing ventilation rate by X changes health, this particular health thing. There have been many small scale studies and intervention style that generally show that if you ventilate better, you get better health outcomes. But then you can't quantify it to a great amount of detail, and every study, of course, looked at a different aspect of health, and every study had a subtly different way of thinking about ventilation. So they're not exactly comparable, but there's a considerable weight of evidence from many studies over many years in many kinds of apartments looking at many health effects that ventilation does indeed have an impact. The impact is highly variable depending on the population you're looking at and the health impact you're looking at and what you mean by more and better ventilation. So the results are all over the place. But generally speaking, there's enough data out there that we can reach some sort of reasonable guidance, if you will, on what is good practice. And that's kind of where we're at right now in the indoor air quality business. Is a lot of it is what I would call slightly indirect, but there's plenty of evidence out there. It's just not, here is the right number style evidence. And frankly, it never will be, simply because people are highly variable. We're never going to control emissions that tightly. There's always going to be some squishiness with these numbers. but we're doing the best we can with the information that we have, and that's where we are.
Ian, thank you so much for presenting today. From the questions, you can tell that you've generated a lot of discussion. We're sorry for the folks that we couldn't respond to in the time that we have today, but we hope you take another minute and stay with us and complete our survey. But thank you, Ian, and do you have any closing remarks before we start our survey?
No, I'd just like to say thank you to Building America for hosting this, and thanks to everybody who tuned in today. Hopefully this was constructive, and people have a reasonable idea about why this matters for high performance homes and some of our alternative strategies for ventilating well.